Hi, this video is going to be done much faster than the other videos, but you can pause and look at it and try to understand. Here we go. You have a 9-volt battery and you wish to apply a voltage of only 4 volts. How would you connect them? The 1 ohm resistors to make a voltage divider. Well, all you got to do is connect them in series and tap the voltage from the first one and the fourth one, in which case you will get 4 volts, because the total current would be 1 ampere, and therefore the voltage across the 4 ohm resistance would be 1 times 4, which is 4 volt. Similarly, the voltage across the 5 ohm resistor, that's if you had tapped the connections from here and this point, it would have been 5 volt. And that is why this arrangement is called a voltage divider, because it divides the voltage into 2 parts. In the second one, 8 identical bulbs are connected in series across a 110 volt line. What is the voltage across each bulb? Remember that because they are exactly identical, the voltage drop will be the same across each one. So 110 divided by 8 goes 13.75 volt. And to find the resistance, just divide the voltage across each one by the current drawn by each, which is 0.42 ampere. And the power dissipated is given by the product of voltage and current, which is 5.78 watts. Whenever you're given an equivalent, or whenever you're given a circuit, and you're asked to find the equivalent resistance, the easy way to check whether it's in series or in parallel is to look at the currents. See, for example, surely when the current flows through this part and when it reaches this junction, the current is going to split into 2 parts. So one part is going to go through this, and another part is going to go through this. So which means the currents flowing through the 680 ohm and the 820 ohm are not equal. If the currents are not equal through 2 resistors, then they are in parallel. So now 680 and 820 are in parallel. So first find their equivalent resistance, and then that resistance could be regarded to be connected in series with 960 ohms. Oh, this got to go. Okay. I've done it all in one step, because when you try to find the equivalent of parallel resistors and you only have 2, you just take the product divided by the sum. That's what you find here, and then I've added it to 960. In the B part, you have to find the voltage across each resistor. So find the total current first. That is the current that starts out from the battery. And once you get that current, you can find the voltage across each resistance by multiplying the current with the resistance. Since this whole current flows through 960, we just multiply that with 960. You get 8.65. And remember that because 680 and 820 are in parallel, the voltage across them will be the same. And of course, if you already got 8.65 dropped here, then the remainder of 12 should be dropped across the other 2, which is 3.35 volts. Once again, in this circuit, you're asked to find the net resistance. And here you have to make out that the current flowing through these two resistances will be the same. So they are in series. Add them up and you get 2R. And then because you see the dots here, A and B, that combination is in parallel with this. And then you continue looking at energy that this resistance is going to be in series with, the combination of the three, and then the whole thing is going to be in parallel with that. And then the equivalent of this whole group is going to be in series with this. So that's how you figure out. Okay, so all this needs to go. Sorry for that. Okay. So since the top two are in series and parallel to R3, I'm just doing all that in one step. You get 2R by 3, and then taking 1, 2, 3, 4. Remember the fourth one is in series with that, so add it. And then that combination is in parallel with the next one with the okay. So you take the product by the sum. And finally, after you get this, the combination is in series with the last resistance, which is this one. So you just add the 5 by 8 R with the R, and you get 13 over 8 times R. That's the answer. Two resistors connected in series to a 110 volt line uses 1/4 the power that they would consume when they are connected in parallel. One of the resistors is given as 3.8 kilo ohms. What is the resistance of the other? Set up two equations. This is how they look when they're connected in series. Of course, it's an alternating voltage source. And when they're connected in parallel, they look like this. And then you try to compare the powers. The power in series is 1/4 power in parallel. The voltages in both cases are the same, so we're going to use the formula for power that involves voltage and resistance, of course, because you have three formulas, and we should be smart in knowing which one to use according to the situation. Now in this case, knowing the voltage is the same, this is what we use, and then we get the resistance in series is 4 times the resistance in parallel. And we know that the resistance in series, just the sum, and the resistance in parallel is the product divided by the sum. So translate that into math, cross multiply, and you would get a quadratic equation. When you collect all those terms to one side, that's what you get. But you can solve this by completing the square, because the middle term 7.6 could be split into two parts, and so you get the unknown resistance as 3.8 K. So actually the two resistors have the same value. In the sixth one, you're asked to find the potential difference between points A and D. Now this is Cookoffs' laws that you have to apply, and when you look at junction A, surely I3 is flowing in, I1 and I2 are flowing out. Therefore I3 is equal to I1 plus I2. Then in the top loop, as you go through the top loop, in the clockwise direction. Negative 34I1 plus 45 minus 48I3 is equal to 0. And when you go through the outer loop, let's say again the outer loop, minus 34I1 plus 19, that's 18 plus 1, 19I2 minus 75 is equal to 0. So you got your three equations. Now you got to solve them. In order to do that, I'm rearranging this equation and make I2 the subject. So I get I2 in terms of I1. And once you get that, substitute into equation 2. And I'm just rearranging that first. And I make I3 the subject from that equation. You can solve it any way you like, but this is what I'm doing right now. So I get I3 in terms of I1. So I got I2 in terms of I1 and I got I3 in terms of I1. So I can substitute both of this into equation 1. So in place of I3, I write this whole thing. And I1 I leave as it is, and I2 I write this whole thing. And you have to be very careful in trying to solve this, because if one sign goes wrong, then the whole answer is screwed up. So you have to be careful. So finally you get I1, and once you get I1, substitute it into this equation for I3 and you get the value of I3. And then you can plug it back into that equation to get I2. I am trying to finish all of this in one screen so that you can see all of it in one place. Take a good look at this and try to understand, especially how to set up the equations. And in the second part, this asks you what is the terminal voltage. In fact, it says you have to find the potential difference between points A and D. Go back to the figure, look at A and D, and you just find the potential difference in that path. So if you go across AHD, that's what you get, 34I1. That's the potential drop, 34I1, right? If you go across ABCD, you get 48I3 minus 45. So as you go from A to D. So I found it in two ways. I'm trying to show you that because those two branches are in parallel, whether you go AHD or whether you go ABCD, you are supposed to get the same potential difference. And sure enough, I showed you that in both cases you get 29 volts. And then in the C part, to find the terminal voltage, the terminal voltage of the battery there, you know, it's a 75 volt battery, but there is a current of I2 times 1 flowing through. I mean the potential drop of I2 times 1. Because 1 is the internal resistance of that battery. And for the 45 volt one, its internal resistance is 1 ohm. That's why that is shown along with it. That is not a separate resistance. So both the terminal voltages are slightly lower than the EMF, as we know. And in this question, you have to find the magnitudes and directions of the currents through R1 or R2. Again, got to apply Cookoffs laws. take the currents as I1 and I2 in the lower branch. As you go counterclockwise, V3 minus 18 I2 is 0, and that is 6 minus 18 I2 is 0, so you get I2. And then as you go counterclockwise in the outer loop, you get 9 plus 18 I2 minus 22. Actually, you're going not the outer loop, I'm sorry for that, you're taking the top loop. Minus 22 I1 is equal to 0. Let me just explain that, because you're going from negative to positive, that's why it's positive 9. And then you're going against the current, so it becomes positive 18 I2. And then you're going with the current, so it's negative 22 I1 is equal to 0. And substitute the value of I2 as I've done here and solve for I1. So since you got both I1 and I2 as positive, that would mean that the assumed directions of the currents were correct. So the currents are flowing as shown in the diagram. And the magnitudes are 0.33 ampere and 0.68 ampere. In the 8th question, once again, you have to find the magnitudes and directions of the currents. Now, let me take that out. So again, it's an application of Cookoffs' laws. And very carefully, if you apply the laws, you're going to get it. Let me clean up this mess. And I2 is I1 plus I3. Because I've already done 2 problems, I'm going to let this run quickly. Now you see the directions of the currents, I1 and I2. The equations are given, and you have to solve the equations. You can take some time to look at this and try to understand this. And like I said, because I've already done 2 questions of the same type, I just want to go ahead with the remaining questions. This is one of the easiest questions. Somebody used a 5 microfarad capacitor instead of 16. How do you correct it? Quite simply, put 11 microfarad in parallel with that, because 5 plus 11 gives you 16. This is a good question, that you have how many? 4 capacitors actually connected as shown in the diagram, and the capacitances, all 4 are given, and the charge on the third one, Q3, is given. You got to find the charge on each of the other capacitors. What you have to remember is, whenever capacitors are connected in parallel, like C1 and C2, if you can make it out, because they are in parallel, the voltage across them will be the same. So too, the voltage across C3 and C4 will be equal. So voltage is given by Q by C, and you can use the idea that Q3 by C3 now should be equal to Q4 by C4, because C3 and C4 are in parallel, the voltages are equal. So you can find Q4. We started out that way because Q3 was given. Now we also know that the total charge on Q3 and Q4 should be equal to the total charge on C1 and C2, because those two branches are in series with each other. And that we know as 69 now, because 23 is already given. Now we know that 46 is the other one, so the total is 69. And once again, because the capacitors C1 and C2 are in parallel, the voltage across them should be equal. That's V1 is equal to V2. And that gives Q1 by C1 is equal to Q2 by C2. Substitute for Q2 and solve, you get Q1. And once again, finding the voltage. Across V1 and V2 should be the same. V3 and V4 should be equal. And therefore the voltage across VBA should be the sum of the two, which is 5.75 volt. Because the potential difference adds up. Why does the potential difference add up? Because you see that the positive plate of C1 and the negative plate of C1 will be connected to the positive of C3 and to the negative C3. So the voltage just adds up. They are increasing the potential difference. This again is a direct question. You have three capacitors. How will you form the maximum and minimum? To get the maximum, you obviously put them in parallel, and to get the minimum, you put them in series. So it's a straightforward question. And this number, don't worry about that. Okay, maximum in parallel, because you just add them. And I will let this go fast too. And the minimum is in series. So just use those two formulae and just finish it. We'll get to the next question. Some of the capacitors, because when they are connected in parallel, it says it's 35, and in series it is 5.5. So you set up two equations. Well, and substitute. I'm trying to keep this video under 25 minutes because it's a must. And then you solve them, you get it. It's going to be a quadratic equation and you have to solve it. Excuse me. Now, two capacitors are connected in series to a 12-volt battery, and later they are disconnected and connected directly to each other. It says positive to positive, negative to negative, meaning that they are connected in parallel, and you got to find the charge on each capacitor. Remember that the total charge will be the same. So what we're trying to do is find the equivalent capacitance in series, which is the product by sum. So once you get the capacitance and you know that it's connected to a 12-volt battery, just find the charge. So the total charge here is going to be 13.82 nanocoulombs, and then when you connect them together, because they are in parallel, the voltage will be the same. And the formula for voltage is total charge by capacitance, and in parallel the total capacitance is just C1 plus C2. When you do that, you get the voltage. That's the voltage on both capacitors, and so to find the charge on each one, multiply this voltage with their individual capacitances. That brings us to the last one. In the RC circuit, how long does it take the capacitor to discharge? So use the formula for discharge of the capacitor. Discharge of the capacitor is given by this formula. And although it talks about voltage, we know it's proportional, so the formula can just be written for voltage as I have shown. It says 0.1%. 0.1% is 0.001. Why? Because it's 0.1 divided by 100. And you have to know that to change the exponential, put natural log on the other side. And when you solve, you get 0.18 seconds. Thank you.